All right, we're going to start our first problem for rigid body momentum. And so what we have here is a capsule off of our rocket. So the capsule mass is 1,200 kilograms. Mass moment of inertia through the center of gravity, 900 kilogram meters squared. So that would be coming out. So this is for an axis perpendicular to the page. It's going this direction at 800 meters per second. All right, though we know we're taking x the other way. Starting from rest. And so here's this capsule's going along, and they're going to fire these thrusters here. So the fire goes this way, but the force goes the other way, right? So we have a thrust duration of 0.3 seconds, and during that 0.3 seconds, the thrust is 400 newtons. And so here we have find the angular velocity after thrust. So here we see velocity time. So this is a momentum problem. All right. So let's figure out, let me just ask you this first of all, when you fire these thrusters, what kind of change in motion do you expect? And if you look at this here, the relative to force, you have the force going this way, the force going that way. They cancel each other in the x and the y. They're just a little bit off center. So what this is going to cause is rotation, but in terms of along the x, or if we had along the y, the sum of the forces is 0, so the change in acceleration in the x or the y will be 0. All right, so here is, we're looking at, basically we're going to be affecting a torque here, is what's going to be happening. All right, so we're looking at rotation, starting from rest in terms of rotation. Yes, the thing is moving, but relative to the rotation, it's at rest, so h1 is 0. Then we'll take the sum of the moments about g, and that'll determine h2. So what are the moments about g? Well, there's just two forces. So if we take 400 cosine of 15 degrees times 1.5 meters from there to there, or from g to the outside. So here we have 400 cos 15 times 1.5, that's the moment, times 2, because there's two of them. Fired, and these are constant, so these aren't a function of time, so we can just factor that out, and all you get out from the integration is the 0.3. Equals, all right, what do we have on the other side? H2 will simply be, because we're just looking at pure rotation, all right, and we're doing it about g, so this will just be Ig omega, okay? The other term doesn't show up because that involved R from O to G cross Vg. If you're doing this at the center of gravity, all you have is the I omega. So there's the mass moment of inertia, there's the omega, solve, and we have omega equals 0.386 radians per second. Okay?